And we're back. Hey, guess what? It is time for section 3.4. We're starting with a little bit of triangles, just a smidge, just enough to get you interested, and then we're going to switch to something else. But it's okay, because what we're switching to that's elsewise is pretty fun to do. So triangles are pretty simple, and I think you probably know most of what we're going over today, but we have to go over it anyway. So let's start with the definition of a triangle. Oh, where's my yellow ad? Because it's the definition. So the definition of a triangle is a figure formed by three line segments connecting three non-collinear points, which means they're not all in a line, but I know you knew that. So this is my triangle, and I wanted to let you know that we can label this a bunch of different ways. By the way, that's a symbol for a triangle, so obviously I'm going to draw that instead of writing the word triangle every time. So I could write this triangle a bunch of different ways, but it basically means that I'm using the 3 points to call it by. Now, when this is something you might not know, I'm not sure, when you're talking about a triangle and you're talking about the sides of a triangle, they are all lowercase letters, and those lowercase letters should be the exact same letter as the angle opposite it. So this is a capital A for that vertex, so opposite that side would be my lowercase a. Capital B for this vertex, opposite that side is my lowercase b. Capital C for this vertex, opposite that side is my lowercase c. So that's the way the sides get named, and they have to stick with those. Every book sticks with those. So when you're talking about the sides of a triangle, just understand that you use the opposite letter to get that side. Now, back to the information I'm pretty sure you already know. You can classify triangles two different ways. You can classify them by sides, or you can classify them by angles. You have to know both. I know, right? So over here, if we're doing it by sides, you can have an equilateral triangle, which means all the sides are congruent. You can have an isosceles triangle, which means two of the sides are congruent. Or you can have a scalene triangle, which means none of the sides are congruent. That's okay. We're not upset about it. By the way, all of this stuff, definition. So, or you can classify them by angles, which means we're talking about the angles of the triangle, not the sides of the triangle. Now, once again, just in case somebody gets upset, because I've had students have really serious issues with this in the past. When I'm talking about C, angle C, I'm not talking about this spot or that point. I'm talking about the space in here. That's what angle C is, the space inside those two rays. When I'm talking about a side, I'm talking about the line segment that connects two things. So when we're classifying by sides, we're classifying based upon the line segments. And when we're classifying by angles, we're classifying by the space it takes in between the rays of each of the triangles. Okay, so over here, equiangular means that every angle is congruent. Having a right triangle means that there is one right angle. Having an obtuse triangle means there has to be one obtuse angle, or an angle between 90 degrees and 180 degrees. And having an acute triangle means that all of the angles are less than 90 degrees. They're all acute angles. That was simple enough, right? So I got this really cool thing to show you. Okay, you may not be impressed by it. I was astounded by it when I was your age. Honestly, went home, tore up tons of paper just playing with this one thing, okay? So here is my lovely piece of paper. This is not what you do with your origami paper, okay? This is demonstration, something you can do. I could do it with white paper, but when I tape it up to the board, it's going to be kind of hard to see it if it's white paper. So colored paper, and this was colored paper I didn't really care about. That's why we're using the ones with the cherries on it. See, it's cherries. Okay, so back to the the story. Obviously, you could tell I didn't do a great ripping job on it over here. That's why I don't mind using this paper for it. But I need to have some clean lines. I need a good corner. So I'm going to cut out a triangle. La, da, 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 da. I'm not measuring my triangle. Don't really care what it's like. In fact, just for that, I'm going to make sure that it is a scalene triangle. I'm trying to make sure it's a scalene triangle. Hold on. I can do this. There we go. Scalene, not isosceles. So, different sides. You can tell by looking at it that it is a right triangle. I cut it from a square on purpose, but it does not have to be a right triangle for this to work. Do you want me to make sure that it's not a right triangle? Is it going to make you feel better? I'll do it with another one in a minute that's definitely not a right triangle. Okay, so we have this triangle here. You ready? Okay, so when I take this triangle and I rip it apart, I want to rip the vertices. See, this is one of mine. Hold on. Ta-da! With tape. I want to rip the vertices apart. That's one of my vertices. Still same triangle. See, no tricks here. Ripping the other two vertices apart. La da da da. Tape. Tape. It's magic that way. If I were to line these up against each other so that my vertices are together, you would find that it forms a straight line. Look at that. Isn't that magic? It's a straight line. Okay, let me explain. So there is a thing that says a thing. It's a thing. Respect the thing. There is a thing, theorem 3.11, that says that all the angles of a triangle add up to 180 degrees. That's why it forms a straight line. Because it doesn't matter what triangle you have, you're always going to get a straight line when you line them up. Then you got to make sure it's your vertices that you're lining up. But I know you're just a little bit skeptical. It's okay. It's okay. I'm leaving my tape. Okay, this isn't quite as easy as it looks. I'm leaving my tape up here. But taking these three and putting them right there. I'm not going to touch them again. Well, I will when I show you that it's really not the ones that I'm going to get from here. I'm going to do another triangle. It is obviously not going to be a right triangle. See? Triangle. No right angles here. Obviously, no right angles here. In fact, it's a congruent. It's a acute triangle. So once again, I'm going to rip all my vertices apart. It helps if you stick your tongue out. Ta-da! One. Going to put it right there. That's how you do it. 2 and 3, incidentally. Going to line up my sides so that my vertices do touch. Is a reach for the tape. Vertices do touch and it's flush. And look at that, it's another straight line. I told you every single time. It's amazing how that stuff works. It's because all the angles in a triangle add up to 180 degrees. And a straight line is 180 degrees. So, since that's the case, you can come up with some of the corollaries that they threw down in there. Like, for example, now I got to get this off the board. Just bear with the talking for a minute. Like, for example, the corollary that states that if a triangle is equilateral, then it also has to be equiangular. Because you can't be one without being the other. It automatically happens. It happens that way because of another corollary, which says if a triangle is equilateral and it's equiangular, then all the degrees of that triangle have to be 60 degrees, because that's how you get equiangular, which means that all of these are also 60 degrees. It all ties together. It's amazing how that happens. So, and the other corollaries are if two angles of one triangle are congruent, then the two angles of the second triangle, then the third angles are also congruent, because they have to be congruent triangles. And acute angles of a right triangle are complementary. That one's kind of cool. That means that this angle right here and this angle right here have to add up to being 90 degrees. Doesn't mean they're the same. We don't know that. But it does mean that they have to add up to 90 degrees. Okay. That took care of that. Now we need to talk about exterior angles of a triangle. And I know you're thinking, what? Hold on. So this is our triangle that we're going to look at. Okay? We have a lovely triangle here, obviously not equiangular or equilateral, because 1 degree is 50 and one of them is 60. We don't know what number 1 is. We don't know what angle 1 is, and we definitely don't know what angle 2 is. But we could figure out what angle 1 is by doing some simple calculations, because we know that 50 plus 60, 50, yeah, thinking too much. 50 plus 60 equals 110. And since they all have to add up to 180, 180 minus 110 is 70. Doing stuff in my head isn't as fun as it used to be. Now it's getting harder for me to think. It just hurts more now. I don't know. Anyway, it is 70. So since we know that this is 70 degrees, it is possible for us to figure out 2 now, because we know that angle 1 and angle 2 form a linear pair. See, it's great when I can throw out these kinds of words, ain't it? So since angle 1 and angle 2 form a linear pair, 180 degrees has to equal my 70 plus whatever the measure of angle 2 is. Which means the measure of angle 2 must be 110 degrees. Which is exactly what the sum of the 2 remote angles were. So what that theorem is actually saying is that the measure of any exterior angle, which is what this is, has to equal the sum of the 2 remote interior angles. And that's because of the whole linear pair thing. That's why it is what it is. So now that you know that, we need to talk about what exterior angles really are. Because I need for you to be able to look at a triangle and say, oh, this has a total of 6 exterior angles, and they are here, 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 and here. So I went ahead and I extended down so that you could kind of get a vision for it. And when I extend this one out, you can see right away that this is the angle that's outside of that triangle. But when you extend it out, it has to be the angle that shares a side with that triangle. So that's why it's angle 2. And if I were to extend this segment out, the one that I put in dotted lines here, it would form this side, or that angle, which is also an exterior angle of that triangle. Now, here's the rub. We have 2 more exterior angles over here. We have this one, and we have this one. Now, this angle has to be 110 because it has to be what that was because they're vertical angles. That hasn't changed anything. But over here, are these going to be 110? No. They have to be whatever it takes to either make up the 180 because it's a linear pair, or whatever the sum of those two are, which happens to be 130 degrees in this case. In fact, they're both 130 degrees in this case. And it doesn't matter whether you got the 130 by subtracting the 50 from it or by adding those two interior angles that are opposite. What they're saying is it's always going to be the case. Now, just because the exterior angle over here for number 2, for angle 2, is 110 because those are the two remote interior angles. Over here, this is also an exterior angle, but it's on a different vertex. That's what makes it have a different number, because when we talk about its remote interior angles, it's going to be 70 and 60, the ones that are far away, not the one that's really close up there. And of course, the other two are going to be this one right here and that one right there, and they're going to be the sum of that, which is 120. A lot of times it's easier to add two numbers together to get a number than it is to subtract, because you have to sit there and think about subtraction a little bit, and adding kind of comes like that. So that's why it's nice to be able to have this tool to say 50 plus 70 is 120 instead of sitting there and subtracting 60 from 180. It'd be different if you were like subtracting it from 10, but you're not. You're subtracting it from 180. 180 is always the magical number in geometry, sorry. Not my fault. Get used to it. Okay, so that explains that theorem, which leads us to, are you ready for this? Classwork and homework. That's right, you heard me. Classwork and homework. So for classwork, here, I'll write it on the board. Help you out a little bit. Oh, page 101. We're back to the book, which is nice. Makes me feel a little bit better. Not very much. Numbers 3, 7, and 22. All those answers are in the back of your book. Don't freak out. Freak out just a little bit, not a lot. And then homework. All the answers are in the back of the book, but these problems tend to be slightly harder than the classwork problems. I know you're shocked. Numbers 5, 15, and 24. Look at that, 6 problems total. I'm just saying, you get off really easy in this class. Wait till we get to algebra 2. Oh my gosh, I'm not gonna like load up the homework. That'll be nice. I love stuff like that. Okay, see you on, I think you're at a weekend. I think I won't see you again until Monday. But it doesn't matter because you won't see me until Monday. Well, that'd be nice. Talk to you later. Bye.